Thank you very much for the introduction. Thank you for the invitation to the seminar. So I will talk about something which sounds a priori very geometric, but there's actually a lot of algebra behind what's happening, and we'll see this appear very soon. But I want to start. I want to start first by saying that all of this is joint work with Lee Fu and Andreas Krug. You can read all the details in this archive paper. Today, I will just be working over the complex numbers because this frees up the letter K for the base field, so I can use it in formulas for integers. So I want to start with some geometric motivation. And the geometric motivation, very quickly said, is we want to understand deformations of Hilb and S, so of the Hilbert scheme of endpoints on a surface. And what is a surface to us? It's going to be a smooth and projective surface, variety of dimension 2. Both these adjectives are important. And maybe you don't have your favorite smooth projective surface in mind if you're more on the algebraic side of things. But I think you have heard of the projective plane, and the projective plane is a very convenient example to include. So we will take as our first example the projective plane, and we can also take something called a K3 surface, and this is actually very easy to define. We can work inside P3, three-dimensional projective space, and then we can take some homogeneous equation. This will cut out the surface, and if we let the degree be equal to 4, we get a quartic surface, and a quartic surface is an example of a K3 surface. This is a kind of surface which is very important in the classification of surfaces. Entire books have been written about the interesting geometry that K3 surfaces possess, and they will be interesting from the point of view of deformations of Hilb and S. And the third example that I want to take is in this big classification of surfaces, a surface of general type. So this is a surface somehow on the opposite side of the spectrum compared to P2. P2 is very easy. I mean, you can do very complicated things with P2, but the surface itself is very easy to define. Surfaces of general type are much harder to study and also much harder to classify. And one example, if you've never heard of a surface of general type that you can keep in mind, is a quintic surface. So if the degree of my surface inside P3 is 1, 2, or 3, then we get a surface that is either P2 or very much like P2. Then in our trichotomy, if the degree is 4, we get a K3 surface. Suddenly new features appear, and as soon as the degree is 5 or higher, we get a very complicated class of surfaces, those of general type. And these three surfaces will illustrate a little bit what is known, or what was known, and what the new results are. So this is going to be the surfaces, and the notation that I already used is Hilb and S, which stands for the Hilbert scheme of endpoints on S. And how can we define this? This thing is a moduli space, scary sounding word. It's one of my favorite words in the English language, but it can be a little bit scary if you're not an algebraic geometer. So what is this thing doing? It is parameterizing certain objects. And so it is parameterizing ideal sheaves. I is an ideal sheaf of the structure sheaf on S, and we want something to happen for the quotient. So this ideal sheaf OS corresponds to a certain Z, which is a closed subscheme of our surface, and we can say certain things about closed subschemes. What do we want is that the dimension of this closed subspace is 0, and that the dimension as a vector space is equal to n. So we will see an example of this in a second. And so the Hilbert scheme of endpoints is the moduli space of length n subschemes. And in case you've never seen this before, we can do an example of this. Also, if n is equal to 1, Hilbert and S is just literally the surface, because we want a closed subscheme which is 0-dimensional and which is 1-dimensional as a vector space. And so this is going to be the moduli space of skyscrapers on our. So this quotient here is going to be the skyscraper sheaf of a single closed point. And so our moduli space is just the surface itself. So the first interesting case is where n is equal to 2. And now two things can happen. The first thing that can happen is that we have two distinct points. And the case where we have two distinct points is somehow just taking what we already knew for n equals 1 and transporting it to n equals 2. If we take two distinct points, the closed subscheme of this is 2-dimensional as a vector space. But, and this is what makes Hilbert schemes so interesting, there's a new feature that appears. We can also have a point, a single closed point, together with a tangent direction. And so at this time we have a single point, but this algebra, this quotient of a sheaf of rings by an ideal sheaf, is similar to spec epsilon modulo epsilon squared, so the dual numbers. And this algebra is 2-dimensional. And so this is what is meant with this dimension as a vector space should be equal to 2. And maybe I should put some scare quotes around this. So this is what it's meant with, it's a 2-dimensional algebra. So this remembers a point together with a tangent direction. Good. And now we can relate the Hilbert scheme of endpoints to something else in algebraic geometry. So what can we do? Oh, my symbol goes in the wrong direction. So what we do is we take a point of the Hilbert scheme. So this ideal sheaf I is a point on the Hilbert scheme, and I'm going to send this to a point on sim ns. And what is this thing? This is going to be the n-fold product of S with itself. And on this thing, we have a group action by the symmetric group, which just permutes the factors in the product. And so what can we do now? If I have an ideal sheaf like this, I can look at the quotient. And what I will do now is I will sum over all the closed points in my surface. And at each of the points, I can look at the length of, so LP stands for length at the point P. And so this is this dimension. So at the closed point, here we have a unique point where something interesting happens, and there the length or multiplicity is equal to 2. And so if our point corresponding to the ideal sheaf happens to be of this type, then the expression here would be 2p. If, however, we have two distinct points, the expression here would be p plus q, because the length is equal to 0 whenever the ideal sheaf or the quotient by the ideal sheaf is not supported at that point. So in this way, we have a map from the Hilbert scheme of endpoints to this quotient. And so we mod out by the symmetric group because we can't remember any ordering on our points. Our multiplicities don't remember any ordering. And what is now the very sad thing, or the very sad state of affairs, is that this quotient, it's a singular variety. So your life is miserable. Singular varieties are hard to understand. I mean, sometimes singular varieties make your life super exciting, but I like my varieties to be smooth and projective, and this thing is singular. So that's the problem. Luckily, the Hilbert scheme is actually a smooth and projective variety. So it is of the nicest possible type to a geometer like myself. And this morphism, this is a morphism of varieties. It's a resolution of singularities and is the best type of resolution of singularities. It's what is called a creppant resolution of singularities. What this means is not important. It will just be coming back a little bit later in the talk when I will discuss another ingredient. And so now I have set up the notation and we've introduced the main players. The question that I want to answer, so the motivation was, can we understand deformations of the Hilbert scheme? And so if you want to say this in abstract and fancy language, is you want to say something like, can we compare deformation functors? But we can make this extremely down to earth. Here I look at the sheaf cohomology of the tangent bundle on the Hilbert scheme. This is a finite dimensional vector space. I can look at the sheaf cohomology, the first sheaf cohomology of the tangent bundle on the surface. This is again a finite dimensional vector space. How do these things compare? We're all having some fingers on our hand. Can we use our fingers to determine the dimension of this and the dimension of that? It can't get more down to earth than that, really. And so this is what I meant with understanding the deformation theory. I mean, we want to do a bit more, but let's keep it as down to earth as possible. And so let's look at our three running examples. So here we had P2, here we had the K3 surface, and here we had the quintic as an example of a surface of general type. And it's a fun exercise to compute these numbers. This is not very hard if you've done a bit of algebraic geometry, but at least here we see what the initial input is. And the important aspect, this is not automatic in an arbitrary setting, but it's true in this case, is we have this inclusion. So every deformation of the surface, maybe I can write this inclusion implies that deformations of S induce deformations of Hilb and S. And so just looking at dimensions, so I lost my window. Just looking at the dimensions, the number that we're trying to figure out has to be at least this number. And so maybe it's an equality that could be happening. So let's look at what was known in the literature. Barbara Fantecchi proved all the way back in '94, so this result is now 30 years old, proved that under two conditions on the surface. So what we want is that H0 of the tangent bundle, and so this means that there are no infinitesimal automorphisms. So this is a bit like the first Hochschild cohomology vanishing. So this is kind of similar to HH1 being 0 for a finite dimensional algebra. So this is one of the conditions. And then there's a second condition, which doesn't really have an analog in representation theory of finite dimensional algebras. But we can ask if the structure sheaf has vanishing first cohomology. So this is the first condition. There's an OR here. So one of these two must be satisfied. And on top of this, a second condition needs to be satisfied. The global sections of the anti-canonical line bundle needs to vanish. And so this thing here has to do with Poisson structures. The global sections of this line bundle on a surface correspond to Poisson structures. And so under these two or three cohomological conditions, what did she show? She showed that we have an equality. So nothing new appears. And so we have three examples here. Which of the cases falls under this setting? It is case 3. So she showed that for surface of general type, and also some other surfaces where these conditions are satisfied, the inclusion really is an equality. And so at this point, 30 years ago, you might conjecture, oh, maybe it's always an equality, but you would be unwise to do so, because actually back in, I didn't write this here, but already back in 1985, Beauville looked at Hilb and K3, and he showed that, maybe I can write here Van Teki, and then here we have Beauville, 1985. He showed that this number is actually 21. So it can be a strict inclusion. But his proof is very specific to the case of K3 surfaces. This thing is a Calabi-Yau variety, and so computing this deformation theory is actually just a Hodge number calculation in that case. But that's a very specific situation. Hitchin, however, so maybe this is case 2. And then 12 years ago, Nigel Hitchin showed that if you just assume this first vanishing condition, so it's the same condition as over there, if the structure sheaf has vanishing first cohomology, then the vector space that we're trying to understand is the vector space we know is always there. But if you've been paying attention to how I give this talk, you see a yellow blob. Yellow blob means something is missing. And so the thing that is missing, I mean, something must be missing because we went from 20 to 21. The something that is missing is these Poisson structures. And so on a K3 surface, this thing happens to be the structure sheaf. And so the global sections are one-dimensional, explaining how we went from 20 to 21. And so this corresponds to cases 1 and 2. We already did case 2, if you like, by the specific result of Beauville. But so now for case 1, you really have, we need this result of Hitchin, and the number is 10. So then there is a 10-dimensional space, vector space of Poisson structures. And so this new ingredient are these Poisson structures or non-commutative deformations. So let's go back to a claim that I made here. So what we see here, so I said we have this inclusion because deformations of the surface induce deformations of the Hilbert scheme, but non-commutative deformations of the surface also induce deformations of the Hilbert scheme. But there was still this condition. And sure, we can cover cases 1, 2, and 3 now, but there are other surfaces out there which do not fall under any of the conditions that we've seen so far. And in the paper, the main team, so there are, however, surfaces that do not fit anywhere yet. They will fit there in a second. For instance, the class of surfaces that I had in mind when we started working on this were bielliptic surfaces. These are surfaces that you can get by taking the quotient of 2 elliptic curves with a certain finite group. Geometric details are not important, but these are really important surfaces which are sitting in the same position as K3 surfaces. So K3 surfaces are a very important class of surfaces, and they are what is called of Kodaira dimension 0, and there's 3 other types of surfaces in that very tiny world of Kodaira dimension 0 surfaces, one of them being bielliptic surfaces. So none of the results so far applied to bielliptic surfaces, and I can now state the answer to the question. The thing we're trying to compute is the thing we know is always there, the thing which is suggested by Hitchin to be always there, And then there is a third component, and this is going to be the global sections of the tangent bundle, tensor the first sheaf cohomology of the structure sheaf on the surface. And so we nicely see how the conditions in Hitchin's theorem and Van Tekke's theorem were killing this component. So the nice thing is that by taking the tensor product, we get the answer to the initial question. Good. So this was the geometric motivation and a bit of background on Hilbert schemes. Now I want to talk about how one can prove this result. And this is where something called Hochschild-Serre cohomology comes into play. This question and the answer a priori has nothing to do with Hochschild cohomology. It's a very geometrically phrased question and answer, but Hochschild cohomology has something to do with deformation theory, and by looking at things from this perspective, we will be able to get the answer. And Hochschild-Serre cohomology is a generalization of Hochschild cohomology and Hochschild homology. We're generalizing both of them at the same time. By no means is this a new notion. This existed 20 years ago, at least 20 years ago, but it didn't have a name. And it wasn't used that often since its introduction. So we just needed a good convenient name for this. And so we thought that Hochschild-Serre is a good name for this. And we will see by defining it why it's called Hochschild-Serre. So you can define this for an arbitrary smooth and proper DG category. But let's first define it for a variety. And so what do? We take the self-extensions on x times x. And what do we do here? We look at the structure sheaf of the diagonal. And now we take the canonical bundle. We tensor it with itself k times. So there's two indices here. There is a j and a k. So the j appears in the x and the k appears in the tensor power. And then here we do this, we shift this by k times the dimension of x. And this looks a little bit like what happens with Hochschild cohomology for a finite dimensional algebra. Hochschild cohomology of A is self-extensions as an bimodule of A with itself. And so the enveloping algebra in representation theory becomes x times x in algebraic geometry, and the A as a bimodule becomes the structure sheaf of the diagonal because both represent the identity functor. Tensoring with A doesn't do anything, and the Fourier-Mukai functor associated to the diagonal is just the identity functor. So this is the analogy that we can see. The problem with trying to define Hochschild-Serre cohomology directly for an algebra is that the Serre functor for an algebra usually is not just a bimodule, but it's a complex of bimodules. So your situation becomes slightly more complicated. And so to define this for a finite dimensional algebra of finite global dimension, you can just best take the perspective of a smooth and proper DG category. So let me maybe define this here. The Hochschild-Serre cohomology of a smooth and proper DG category. This is going to be extensions as a bimodule of my DG category. And then here I take A, and then here I take the Serre functor composed k times with itself. So under this smooth and proper condition, we can define the Serre functor, and we can define this now in this complete generality. And the reason, by using the composition in the derived category of x times x, or in the derived category of the enveloping category, this thing becomes very easily a bi-graded algebra. And if we let k be equal to 0, So we're putting the structure sheaf there, or we're putting the identity functor there. We get back the Hochschild cohomology of X. And if we let K be equal to 1, so here we put just push forward along the diagonal of omega X, we get the Hochschild homology of X. And for every other K, we have something which can be of interest, and it will be of interest in what we're going to do later. And what one can show, or is in the process of being shown by Lie Fu and some collaborators, is how this thing is naturally a Gerstenhauer algebra. And this implies, for instance, that the pair Hochschild cohomology and Hochschild homology is, a Gerstenhauer calculus. That was the wrong word there, Gerstenhauer calculus. So this thing and the additional structure on this Hochschild cohomology really encodes lots of interesting invariants of a variety or a DG category. And one can show that this is a derived invariant. And this brings us back to the geometry, because we had this Hilbert scheme of endpoints being a resolution, a crebant resolution, whatever that may be, of the symmetric power of the surface. What we can do now is we can alternatively look at sim n s, but we put some square brackets around it. And this is the quotient stack. So we take the n-fold product of S with itself. We have this symmetric group acting on it, but now we take something which might scare you off a little bit. We take the Lie-Mumford stack, which is the quotient here. And the important result is that there is a derived equivalence. It was very brief in my notes here. The derived category of this Hilbert scheme is equivalent to the derived category of this Lie-Mumford stack. And therefore, the Hochschild-Serre cohomology of this thing is also the Hochschild-Serre cohomology of this thing. And in case you don't already know why we would maybe care about Hochschild cohomology, the thing we are trying to compute is in fact a summand of the second Hochschild cohomology of the Hilbert scheme. And so this is something that is following from the Hochschild Kostant Rosenberg theorem. And because it's a derived invariant, it is therefore also something living in the second Hochschild cohomology of this Lie-Mumford stack. And so maybe, a priori this is not clear, but maybe we can try to compute this and gain information about this. And by this point, you understand that I've been Chekhov and I've been hiding my gun, and everything is now coming together because we have something called the orbifold HKR. This is a result due to Rinkin, Calderaro, and Havlicek. And the setup for this is we have a finite group acting on a smooth variety. It doesn't quite have to be a projective variety, but it will be in our case. And their statement is that the Hochschild cohomology of such a quotient stack is given in terms of some data involving the group. So we take a direct sum over all group elements. We, just like in the HKR decomposition, sum over the indices P and Q, summing to our degree. And then we look at HP and we subtract by CG. And what is CG here? CG is the codimension of XG inside X. So whenever we have a group element, it acts on X. It moves around a bit. There's going to be a fixed locus. This is going to be a closed subvariety of X itself. This thing has a codimension. And that's a number. And we can use that number to put it in that cohomological degree. And then we look at some sheaf cohomology on the fixed locus. Maybe I should have said that this is the fixed locus. And then we take wedge Q of Txg. And this is something we recognize from the HKR decomposition, but we have to slightly twist this by an omega g. And what is omega g here? This is the determinant of the normal bundle. Don't worry, I'm just stating this to give you a flavor of the statement. We're not going to do many calculations with this. And then finally, G is acting on all of this. We take the co-invariance. So this is a result which was published 5 years ago, and it's an easy, from their results, it's not very hard. I mean, it's just an easy exercise, essentially, to extend this to a decomposition for all of the Hochschild cohomology. And this is important. Everything I've said here is purely as vector spaces. Oh, suddenly it started raining here. This is all just as vector spaces. There is an interesting Gerstenhaber algebra structure on the left-hand side of this thing. We don't know what the Gerstenhaber algebra structure on the right-hand side is. Or rather, what we cannot do is construct a geometrically meaningful Gerstenhaber algebra structure on the right-hand side and compare them. Even defining the product structure is a very hard problem, let alone comparing the structures on both sides. So this is purely as vector spaces, but for our purposes, this is enough. And so now I'm going to condense 15 pages of algebraic geometry in our paper into 3 lines. What are we going to do? We're going to do all of this for the action of the symmetric, group acting on S multiplied with itself n times. And the important trick now is that you don't want to do this for every single n. You want to do this for all n simultaneously and combine this into one nice formula by suitably reassembling things. So this thing here gives a decomposition of the Hochschild cohomology and also the Hochschild cohomology. And by doing this for all n at the same time, you can combine this into a single formula. And so what do? We want to compute the Hochschild cohomology for a fixed k. I'm going to write the formula in this shape of the Hilbert scheme of n points on S. And we want to do this for every n. So we're going to sum over all the n, and we're going to put that graded vector space in front of the coefficient t to the power n. So this is the thing we're trying to compute for every n. And the nice thing is that we can take a sum over all the indices I, at least one. We take the Hochschild cohomology of our surface, and we introduce an interesting shift of the grading. I mean, maybe I am going to use red for this, because this is really the interesting thing, in my opinion. We have this funny grading shift. And we compute this for the surface. We put this in front of t to the power I. And the last thing we do is we take a big graded symmetric power of this infinite dimensional vector space. And we were interested in the second Hochschild cohomology of what's happening for the Hilbert scheme. And so this is the k equals 0, j equals 2 Hochschild cohomology. And what do we get on the right-hand side? If we just collect what is happening in the appropriate degrees, we get the second Hochschild cohomology of the surface, we get the wedge 2 of HH1 of the surface. And we get a third ingredient, which is really the new novel ingredient. It is the K equals -1 Hochschild-Sterk cohomology in degree 2 of the surface. So this is where this interesting grading shift happens. We're really looking at all of the negative. I mean, it's bi-graded, so what does negative really mean? But all of the negative Hochschild-Sterk cohomology comes into play. And so now to get the complete answer, we still have to compute this and this so that we can match up these two things with what this formula is telling us. And then we can cancel those contributions we don't care about. We can cancel them out and we get the answer that I wrote above. And so to get the calculation for the second Hochschild cohomology, so the second global, second sheaf cohomology of the structure sheaf, you can just take the invariance. This is an easy calculation. And to compute the global sections of something like the wedge 2 of the tangent bundle, there's a result by Boissière. But the interesting thing is that this result of Boissière is a correct result, but he conjectured something that would have implied our answer, but his conjecture turns out to be wrong. So maybe I didn't explicitly say this. So Boissière conjectured back in 2012, I think, a formula which would imply our result. But a few years later, counterexamples were found, and it wasn't clear how to fix Boissière's conjecture. So what does Boissière's conjecture do? Here are a left-hand side and a right-hand side. And so what are we doing here is we're looking at some dimensions of some vector spaces. And so HPQ, these are Hodge numbers. And we twist them by a line bundle. So twist by Ln. And what is Ln? Whenever we have a line bundle on the surface, we have an induced line bundle on the Hilbert scheme. And so we can try to compute these things. So our result would be where we let L be the canonical bundle. Or I guess, yeah, well, you know, you have to do it for all K. We do it like this. And the conjecture that he wrote is exactly this thing here, but without the thing in the red. So he conjectured that the thing you're trying to compute only depends on the twisted Hodge numbers, where you twist only by L. But this grading shift, which really depends on the I that you're looking at, can be translated back into the setting of his conjecture, and means that you actually have to take powers of your line bundle L on the surface in order to compute what you're trying to compute. We can't prove this conjecture. Our main result does not prove this conjecture either, in the special case where L is omega s, except in some low degree cases. So because this procedure here that we did here by computing things and then trying to cancel, it only works at sufficiently low degrees. So we can't prove Boissière's conjecture in generality. There are in the paper various specializations. So there are here, this is the power series in x, y, and t. Well, it's polynomial in x and y. It's a power series in t. If you specialize say x to 1 and you let y be general, we can prove the result. If you let x be equal to y, if you let x be minus y. So there's various special cases that we can prove, or which were already known in the literature. And this conjecture, this fixed conjecture, is consistent with all of these. And so this really suggests some HKR-like decomposition for the Hochschild cohomology and more general things on Hilbert schemes of points. So if you like a challenge, this could be an interesting challenge for you. But if you like a more algebraic challenge, let me discuss the final thing in my talk, the Heisenberg. See, we're a little bit faster than I intended to go. If there's any questions, feel free to ask questions. I mean, I still have 10 minutes or so of material, but not 20 minutes. So if there are questions, oh, there's a chat. Okay, yeah, so I don't want to claim, let's say, that we were the first to introduce this. We can't find this except in, so this is discussed, for instance, in a paper by Orlov, where he discusses derived invariance of the canonical algebra. And so I can certainly imagine that this thing was going the rounds in the Moscow School of Algebraic Geometry 30 plus years ago. But as far as I can tell, it never received a name. And that's why we just call it Hochschild to give it a name. But as I said in the beginning of my talk, by no means do I claim that we were the first to consider this. We were maybe the first to give it.
I'm not complaining.
Okay. Okay. Yeah. Good. So the final thing now is, so I mentioned that our result is really where we want to let L be some power of the canonical bundle. But let's take the easiest case. Let's take the structure sheaf. And this Boissière formula, then really, so the Boissière formula really is about Hodge numbers. So the Boissière conjecture is really about Hodge numbers. And in that case, it's a theorem. In that case, it's a theorem due to Goethe that if you put the structure sheaf here and the structure sheaf there, you get an equality of this shape. And the nice thing of putting the structure sheaf there, of course, is that L to the power k just stays the structure sheaf. So that's why this situation is slightly or significantly more pleasant to think about. And the abstract perspective on this identity for Hodge numbers and Betti numbers that Goethe proved was obtained by Nakajima and Grojnowski. And what is their idea? What they do is they look at the singular cohomology of all these Hilbert schemes taken together. So the idea of taking all of these things together is certainly not new. This was observed to be a good thing to try by Goethe and then really put into an abstract framework by Nakajima and Grojnowski. Because what is the thing they do? They construct some really big algebra, the Heisenberg algebra. I will indicate its construction in a bit. And this thing acts on this graded vector space. And it's not just any old module for this thing. It's really a highest weight representation. So we call this the Fock space. And constructing this Heisenberg algebra, acting on this thing, is really the abstract way of deducing this type of equality of numbers. This is an equality of numbers, but it's really implied by having this Heisenberg algebra acting on this big vector space. And this Heisenberg algebra, it depends on a vector space V, and this vector space V is just the singular cohomology of the surface itself. So what we want to do is we want to define an algebra from just the cohomology of S, which acts on the cohomology of all the Hilbert schemes. And so this is somewhat reminiscent of what is happening here. In the left-hand side is the thing we're trying to understand, and on the right-hand side is something which only depends on the surface, although it depends in a funny way on the surface, maybe. And so the data to define the Heisenberg algebra is a vector space together with a pairing. This is going to be the intersection pairing of the cohomology. And this thing is now defined using generators and relations. And just a few minutes before the talk, Severin was talking about a friend who doesn't like definitions using generators and relations. If this friend is in the audience, I'm terribly sorry. We will be defining something using generators and relations now. This thing has a lot of generators because we have a generator Pn alpha for every natural number and every element in our vector space. So when I say this is a big algebra, you can see now why this might be a big algebra, because we're summing over an uncountable set of generators here. And then we have Q alpha n. So we have two types of generators, P and Q. And there are certain relations between these things. And so all the P's commute amongst themselves, all the Q's commute amongst themselves, whatever alpha we put at the bottom. But there is an interesting compatibility with the vector space structure, because we could take alpha plus beta inside our vector space, and then the generator, the degree n generator associated to alpha plus beta is the sum from 0 to n. And then here we put p alpha k, and then p beta n minus k. So this is an important compatibility with the abstract structure, the additive structure of our vector space. And the same relation just with Q's instead of P's holds for the other type of generators. And so the one thing that we haven't explained yet is how P and Q interact with one another. And the statement here is that the product Q alpha with n and P beta with m is the sum from 0 to the minimum of n and m. And here we take the symmetric power of alpha beta, we take our pairing, and we put p beta, and then we take m minus k, and then q alpha, I hope I didn't mess it up, n minus k. Maybe I had a typo somewhere, but this gives you a flavor of this algebra. It's an algebra defined purely in terms of something which happens on the surface. And it really controls all of the singular cohomology of the Hilbert scheme. And why am I now talking about the singular cohomology of the Hilbert scheme? Well, if you know something about the singular cohomology of the Hilbert scheme, again, by the HKR decomposition, and maybe I should also phrase the Hodge decomposition, we know something about the Hochschild homology of the Hilbert scheme. And there is some recent work by Gyenge, Logvinenko, and who's the third one? Gyenge, Logvinenko. Who's the third one? Let me quickly Google. Gyenge. I want to attribute it to everyone, not just to those two. Koppensteiner, yeah. There is, I can phrase this here. So in which order do they appear? Gyenge, Koppensteiner. what they did is they took this Heisenberg algebra and turned it into a Heisenberg category for every smooth and proper DG category. And this should, I think, imply, with some additional work that needs to be done on the Hochschild homology of symmetric powers of the DG categories, should imply a way to compute the Hochschild homology. Maybe I'll put a question mark. Should imply a way to compute the Hochschild homology of sim n of A, where this thing is the Ganter-Capran of symmetric power. And the thing now, the formula that we have here, this symmetric power appearing there, is very reminiscent of what is appearing in this Heisenberg picture and this Fock space picture. So the question is there something similar where there's a certain Heisenberg algebra acting on the Hochschild cohomology of all the Hilbert schemes, or maybe even the Hochschild-Serre cohomology of all those Hilbert schemes? And I would be very interested in knowing the answer to this, because I don't have anything remotely like a partial answer. I can just tell you why it is very hard, I think, to prove this. There's two problems, at least two problems that I can see. The first one is a problem that happens whenever you work with Hochschild cohomology. So Hochschild homology is really as nice as you want. Whenever you have functor between two DG categories, there is an induced map on the level of Hochschild cohomology. But whenever you have a functor or a quasi-functor, whatever setting you want to work in, between DG categories, this in general does not give a map like this. There are situations, or maybe the other way around, I should say, it should be contravariant. So there's no such thing like this. There is, in some cases, and this was done in this abstract setting by Keller, there's this limited functoriality for fully faithful functors. But this is not good enough to get anything like this in this setting of symmetric powers of DG categories. For instance, if you take a K3 surface or a Calabi-Yau category, then all these things will be indecomposable, and there's no fully faithful functors whatsoever. So that's a problem. So lack of functoriality is a problem. And so this approach here by Genge, Koppenstein, and Logvinenko has the benefit that it will imply something like what happened for Hochschild homology for every additive invariant, but Hochschild cohomology nor Hochschild-Serre cohomology are additive invariants. So you cannot just take their really nice input, this idea of having an Heisenberg category acting on symmetric powers of a DG category. You cannot just apply Hochschild cohomology to this, sadly, at least not right now. Maybe there is some extended functoriality which works, but I don't know how it could be obtained. And then the final problem, why this seems to be a very hard question, is that what we are doing, let's scroll up again a bit. Where is it? Here it is. What we are doing here is we are taking different vector spaces together and then take the symmetric power of it. And recall that Hochschild homology was the case where k is equal to 1. And what happens here in this index, if k is 1, we have 1 plus 0. And so the Hochschild-Serre homology, in that case, is just the Hochschild homology. It stays the same over and over and over and over again. And here, if you want to compute something for the Hochschild cohomology or all of Hochschild-Serre, we are taking the symmetric powers of changing vector spaces. We're not just putting the same vector space in front of every t to the power I, and this makes it somewhat incompatible with this Heisenberg algebra setup. And so this raises a question to which I have no answer whatsoever, and to which with which I want to end my talk. Is there something like a Heisenberg algebra in the background of all of this? This here, so the proof was really hidden in these 3 lines, and it's just a lot of bookkeeping to reduce things to this Hochschild-Serre cohomology of the surface. But maybe there is a more conceptual proof that I do not know how it would go. And that is everything that I wanted to say today. Thank you very much.
Yeah, thank you very much for this very nice talk. Are there any questions from the audience?
I have 2. Thanks again for the very nice talk. So as far as I remember, there is also an action if you take the mentioning the Heisenberg algebra actions. So if you take the irreducible representation, I think there's also an action of the Virasoro algebra, right? And you can describe it also geometrically, not in Hochschild, but in cohomology of Hilbert schemes. I think it was done by Manfred Lehnen also some time ago. And I was wondering if this formalism, I mean, it also gives a description of these Nakajima relations. I don't know if this has any relevance for your setting, or if it can be incorporated in any way.
Possibly. I haven't ruled out every algebra yet that appears. I just wanted to say that at least the first thing to consider doesn't work. And if I remember correctly, we briefly looked at the Virasoro algebra, but it also didn't quite fit the setup that we were aiming for. Maybe we didn't try hard enough. That's also certainly possible. But at least for the Heisenberg algebra, we can show that it doesn't fit whatsoever. Maybe the Virasoro, maybe I should try a bit more with the Virasoro algebra. I'll remind myself of this by writing it here.
And the other was more a general question. I mean, this Hochschild cohomology or Hochschild-Serre or cohomology, can you also define it for more general quotient stacks, which are not the linear Mumford stacks or orbifolds? I mean, like Artin stacks.
So the way we define it now, we're page 3, I think. Oh yeah, here. So we are really using the Serre functor. And the problem with things which are not smooth and proper, either as variety or as Deligne Mumford stack or as DG category, is that you don't have a Serre functor per se. And we want to try generalizing it, but we don't have a good definition yet. I mean, last week I was in Oberwolfach and I gave a very similar talk. Sorry, Sibylle and Severin. And then afterwards, Dima Khaledin said, oh yeah, you can try to do this and this should just work. And maybe people have looked at this 20 years ago already. But I haven't been able to try this approach yet. So it should be possible to do this for an arbitrary DG category, I would hope. Because the nice thing is that Hochschild cohomology and Hochschild homology can be defined for anything. You can define Hochschild cohomology and Hochschild homology for a cow, as long as your cow is actually a DG category. And right now, our definition really uses the Serre functor, which requires these nice properties. So defining it for an arbitrary Artin stack would be interesting, but it's not yet done by our work.
Thank you.
Yeah, I also have a question. So I was wondering, the second Hochschild cohomology of the surface is now a direct summand of the second Hochschild cohomology of the Hilbert scheme of points. Is that
Yes.
correct? Okay. Um, and so there's this relationship to deformations of abelian categories of coherent sheaves. Do you have some sense of what the other summands might mean in terms of sort of geometric
No.
terms?
You're talking about these two summands, right?
Right.
No.
Okay.
We don't. I mean, the paper was already long enough, so we didn't
Sure.
try to also answer this question. It's an interesting question, though.
Mhm.
And in particular, we thought about this a little bit in this setting of bielliptic surfaces.
Okay.
Because in bielliptic surfaces, you genuinely have this thing appearing. There is the contribution, the third summand in the answer is something which arises from this.
Mhm.
And we would be very interested in knowing what it is. Also, here I spoke about the Poisson structure. Well, I didn't speak about it that much, but here we have the Poisson structures appearing. So the Poisson structures on the Hilbert scheme, they are smeared out over these two summands. What do they mean? I don't know yet.
I see.
Yeah, so whenever you have a surface, where's my answer? Whenever you have a surface where both of these are non-zero, such as for bielliptic surfaces, it becomes really a question to an algebraic geometer. What is this additional deformation direction? We know that for Hilbert schemes of points on K3 surfaces, this additional deformation direction really gave rise to a massive industry of hyperkähler varieties. Well, here there's another deformation direction, not for K3s, but for bielliptic surfaces. I don't expect an industry as big as the hyperkähler industry in this particular direction, but it's pointing towards something that we don't know.
See. Yeah, nice. Thanks. Are there any other questions? Doesn't seem to be the case. So let's thank Pieter again.
Thank you for the invitation.